Let us now move to the next talk of today's session by Faith Johnson, who is a PhD candidate at Rutgers University. Faith studied for her undergraduate studies at Rutgers in electrical and computer engineering, and she is now a doctoral candidate working with Professor Christine Dana, and her work is in the overall area of social navigation. And today she will speak to us about toward socially aware visual navigation with hierarchical learning. Faith, you have 20 minutes for the talk.
Thank you. Okay. Let me share my screen. All right. So today I'm going to be taking you through, I guess, my most recent paper, which is feudal networks for visual navigation, where we're basically going to be talking about how can we tackle the problem of only navigating based on like RGB input from a camera or an image. But first, before I get into kind of the direction we took, I wanted to give a very brief, very high level, I guess, introduction to how this type of problem has been solved in the past. So if we talk about just like general robotic navigation, the Holy Grail is kind of taking inspiration from how humans learn, which is that as we're walking around, we identify landmarks for like key areas. And then we think about making those as nodes in the graph, and then we kind of have approximate distances between those landmarks that we use for general path planning when we're trying to get from point A to point B. This is great, but way back in yesteryear, that was kind of impossible from a technological standpoint for people to implement directly onto robots. And so what they decided to do was move towards SLAM, simultaneous localization and mapping, right? Where they would basically just make big 3D models of the world around the robot. And if you know the exact XYZ coordinate of every obstacle around you, of course, it's very easy to then plan a path from point A to point B where you're like not running into obstacles and all those things, assuming the obstacles aren't moving. But the issue with this is that, especially nowadays, as we're trying to move towards robots with smaller and smaller systems, this approach is very compute heavy. And it also has a large memory footprint, right? So you can't necessarily implement it in small robots. Also, it requires that you've seen the environment before that you want to navigate in, or that you have some, or that you have like extra time to be able to sit there and like compute the map as you're actually navigating around the space, which isn't necessarily always a given. And so to kind of lighten the computation and memory load for that, people move towards making topological graphs, which is close to the graphs that humans are making, but they're a lot more dense. So basically what happens is as a robot's walking around, instead of making a 3D map of everything that's around the person, they will simply add each node as an image and then record the distance traveled between each image that it takes. And then you can do path planning over that graph. And so that kind of enabled visual navigation to come about. But depending on what spaces you're planning in, those graphs can get very, very large. And it still kind of requires that you've seen the space before in order to actually have a functional navigation agent. So in terms of visual navigation for solving those two tasks, or so solving those two problems, we kind of move towards works like no-RL, no simulation, where instead of building the graph, then planning over the graph, what they're doing is trying to hallucinate what a new node in the graph might look like. So the robot is kind of doing what people are doing, which is when you're walking around a space you haven't seen before, you're thinking, okay, I kind of understand how houses are set up, right? So I'm going to think that if I go around this bend, I'm assuming I'm going to see like a hallway and another door to like maybe a bedroom or a bathroom. And then another work called One for All, which is kind of throwing out the idea of needing to plan over a graph altogether. And what they're doing is basically making a 2D latent space, which is just like a 2D map, right? Where each XY coordinate in this learned latent space maps to a real world XY coordinate and tells you how useful being at that location is for solving whatever task that you want to achieve. So if your goal is navigation, it's saying, if the XY coordinate is on an obstacle, right, it'll tell you, oh, you really don't want to go here because that's not actually like a navigable area in your surroundings. And so for my work, we kind of took big inspiration from these two, but we also decided to take a step back and think about what are kind of the base modules that you would need to even just build a basic navigation agent. And so the first module there is, how do you physically move around, right? If we want to be doing or building an agent that can do these larger navigation tasks, if we're reasoning over like simple motor instructions, it's going to make achieving larger navigation tasks look really, really complicated. So we want to solve that first. And then once that's solved, you then free up space to be able to start reasoning about where should you go? Like now I can move around, but if I have a goal object I want to reach, for example, or a goal location, I have to think about like, is that to the left of me? Is that forward? Is that right? Is it like around the corner? And thinking about the problem on that level. And then finally, there's the top level, which is thinking about what to do if you get into an unwanted state, right? So like I'm backed into a corner and I have to figure out how to turn around, or in a really common case, I'm a robot with wheels and I'm right at the ledge of a set of stairs, right? And so when you think about these three things, we formed a hierarchy of different modules that are working in tandem, each viewing a smaller piece of the overall navigation problem, and then passing their solution down to the next lower level in order to make solving the overall problem a lot easier. And so we can kind of name these things. We have like this high-level manager, this mid-level manager, and then this worker agent. And then in this hierarchy, if you're just trying to, again, build like the simplest visual navigation agent you can, these bottom two squares are all you need for an agent that just explores, right? If you can move around and then you can decide where to go, you can basically explore and map your space. And so this is where we started. We decided to do our experiments in Habitat AI, which is a virtual world with virtual agents. And so that made implementing the how do you physically move around piece a lot easier. We just kind of made a deterministic agent there that accepts commands of like turn left, turn right, go forward, and can execute those in the environments. And then when we started thinking about how to decide where to go, we thought, well, instead of reinventing the wheel, right, we know that humans are pretty good at solving this problem already, right? We've spent ages, years, learning really good navigation policies. And so we wanted to see if there was a way that we could capitalize on that. And so what we decided to do is make this human exploration data set. And so what we did is for different virtual and real world scenes, we dropped people into different environments and then basically just recorded the images, observations of what they would see in the world, and then had them click on a screen to show the direction they wanted to go in, which are indicated here by kind of the red dots. And so for the virtual environments, we did two popular ones, Gibson and Matterport, which are through Habitat AI. And then we also did some real world environments as well. So kind of just walking around campus and collecting these photo point click pairs as humans are exploring. And this gives us good data to be able to learn these navigation policies of humans. And so in this hierarchy that we had before, where we have the human deciding kind of where to go and this deterministic agent that is actually moving around in the environment, with this data set, we then could replace the human with a network that is basically taking in these images and then predicting good places to go in order to just explore. And so let's see some results for how that went. So we called this network that we trained WayNet. And basically what you're seeing here are 4 examples of image observations. And then the ground truth that the human clicked from our data set is in orange. And then the predicted point from our network is in blue. And then if you can see on the bottom row, they usually align very closely. And then for the top row, even when they don't align, the network is still picking plausible places to navigate. So in like the top left, the human decided to go through the doorway that's like directly straight, but the agent decided to go through the doorway that's kind of off to the right of that one, which both are like very plausible places for a robot to navigate to. So we were very pleased with those results. Okay, so then as, I guess, research scientists, we always love to have tasks to kind of gauge how good our networks are. And so we decided to test ours on the image navigation task, which is basically you get an agent, they're dropped in a previously unseen environment, this little guy in room A. They're shown an image of just some goal area that they want to get to. So that would be like a picture of this green box over here. And then they're tasked with finding a path to basically whatever you've specified with that image in the real environment. And so if we wanted to actually achieve this task with our agent, we had to add a few new things. So our original hierarchy is on the left here, but we had to add this notion of a goal into this. So some way to think of where is the goal in relation to me. Instead of, some people are reasoning about that in terms of like, if I'm in a house, what room do I think the goal is most likely to be in? And that's very valid, but we decided to do is, I guess, one step below that, which is thinking about just whether or not I can see the goal in my current image observation. And so to do that, we just used this method called superglue right off the shelf. It appeared in CVPR 2020. And basically what it's doing is scale invariant key point matching. And so what we can see on the bottom here is some examples of 2 images where it's kind of matched or found the object from one image in the other image. So like on the top right here, it found this far away photo of a horse. It found the corresponding matches in the really close up photos of the statue. And so with this, if we're given a goal image, we'll be able to find matches in our current observation to objects in that goal image to help us kind of answer the question of where the goal is in relation to us. And so if we take a step back again, we kind of see that in order to do goal-directed navigation, we kind of have the 3 pieces to make a very rudimentary agent. But in reality, this network has one problem, which is that it doesn't have any notion of memory at all. And so we need to add another piece that looks at, or that at least remembers where the agent has been before. That way we don't, in our exploration, like leave a room, turn around in a circle, and then not remember that we were just in that room before. So then we just go back into that room ad nauseum, right? And so when we were trying to think about how to solve this problem, we decided to frame it as a representation learning problem. And so basically what we wanted to do is contrastively learn a latent space where if you take 2 images and you project them into that space and those 2 images occurred close together in the real world, they would map to 2 locations that are really close together in the latent space. And if the 2 images occurred far apart in the real world, they'd map to locations that are further apart in this latent space. And so the way that we did that is if we use just going through the image goal task again as an example, as an agent is moving around, it will see one image right in room A. And let's just say it gets mapped to this blue dot. And then as it keeps walking around, it might enter room B. And then you can see that image, because it's far away from room A, will get mapped to like this orange dot. And then if it keeps moving and it goes into room C, it might see this image, right, which would get mapped to this purple dot, which is both far away from the room B dot and the room A dot. And then as the agent is moving in each space, what we'll see is that we'll start to form these clusters in the latent space the more exploration is done in each room. And so we can use this notion of cluster density in this latent space that we've learned in order to give a signal to the agent that it might have explored one room looking for the goal enough and it's time to move on. But also where each node gets mapped to in this latent space tells it whether or not it has been there before or if it is seeing a new space that it might be interesting to explore looking for the goal. And so to kind of zoom out and give an overview of kind of all the pieces I've talked about, first we made this human navigation data set where we get observations and point-click pairs to get data of good navigation policies from humans. And then we do this contrastive learning of a latent space that maps images that appear close together in the real world, close together in latent space. And then we, as we go, we use the network that learned that latent space to kind of build what we're calling this memory proxy map, which is basically just the more image observations you have of a certain room, the larger the cluster in that latent space for that room. And so it gives you a notion of how much exploration may be left to do in the current space that you're in. Then we have the network that takes in that map and the current observation, and then predicts basically just a point on the image in a way that mimics the human navigation policies to decide where might be interesting to explore next. And then we have this low-level worker that, based on where that point on the image is, decides to turn left, turn right, go forward, or some combination of those three actions, executes those actions in the environment, gets a new observation for steps 3 through 5 to continue all over again. And I think my favorite part is actually watching it in action. So let's see if this video plays. Okay, so when we're talking about evaluating the image goal task, we have kind of 6 categories. They're either split up into easy trials or straight trials or curved trials, which is that the goal image you're given is either in a straight line of sight of you or it's like around a corner, that's the curved. And then it's split up by difficulty, easy, medium, or hard, which just says how far away the goal image is, where easy is somewhere from 1.5 to 3 meters and hard is from like 5 to 10 meters away. And so if we see some examples of my network, if the goal image that is given is like the edge of the store, we're about to see the agent move around. Whenever it's a blue dot, it's just picking a place. But then when it has the red dot, it thinks that it's found the goal. And then it moves towards that. Or if we're trying to find the corner of that couch, we see it over here. And then if we get to a longer trial where it's trying to find the fridge, and the video keeps pausing. Let's see. We're trying to find the fridge. We see that it goes forward and then eventually finds the fridge and makes a beeline to it. Okay. So just kind of to recap what I've been talking about, we made a hierarchical framework for visual navigation that kind of splits the problem into easier bite-sized pieces inspired by how humans actually attack the navigation problem. We have a new data set for learning human-like exploration strategies and policies. We have a functional image goal task agent that uses this point prediction imitation network that imitates human-like exploration policies. And then the new way of thinking about memory for navigation, where we've reframed it as a representation learning problem. And thank you. I'm now open for questions.
Thank you, Faith. Any questions from the audience for Faith? So let me ask a question, Faith. Have you made any comparisons of the navigation strategies that you have developed with existing schemes?
Yes. So what we did was, and I meant to put it in this presentation, but then didn't do it. Let me see if I can pull it up really fast. So what we did was we basically compared our work to the no RL, no simulation paper, because a lot of the other works that are trying to do the image goal task are using SLAM, which besides using like ground truth odometry, which we aren't using at all, is like really computationally complex, or they're like modeling the semantics specifically. And we thought that NRNS, as we call that other paper, is a more on par fit for comparison. And so basically the way that it is, I guess, reported is, so for each of the trials, straight or curved, and then easy, medium, and hard, they give the success rate. So did you reach the goal that you were given? And then SPL, which is the success rate weighted by the inverse of the path length. So the idea is how much exploration did you do when you were attempting to find the goal? Did you just like go all the way out in an area that didn't matter and meander and then eventually just happen upon the goal? Or did you like did you take the shortest path? And so when we look at that, the bottom two rows are ours. And so when it comes to the straight trials, we pretty much beat NRNS across the board for medium and hard when it comes to success rate, because as a hierarchical method, we really prioritized exploration over kind of just beelining straight for the goal. And then for that also directly impacts the fact that they beat us on SPL, right? Because we are exploring more than this NRNS method is. But that comes back to serve in our advantage for all of the curved trials, where we basically beat state of the art for both success rates of finding the goal and SPL. So we did it in the shorter paths as possible, because all that exploration paid off, so that we were able to like actually go around the corners to find the goals that we were presented with, as opposed to just hoping that we'd be able to see them in a straight line from us.
Okay. A follow-up question. Why did you call it feudal? Feudal.
So,
why do you use the name feudal?
We call it feudal because it's kind of paying homage to like in medieval times when you have like the feudal lords, right? And they like own the land and kind of tell, but don't work the land, and kind of just tell the workers what to prioritize and focus on. But then it's like the worker's job to take that like goal information and then actually execute actions in the environment. And so there's other types of hierarchical learning that is less focused on that direct like manager relationship. So it might just be different agents working at like different temporal scales, but not necessarily like passing pieces to each other, that are trying to give some type of direction to the lower, to the next finer grained network below it. So that's why we chose feudal.
Okay. Another question here. It seems like there may be some part of the underlying system that learns something about the topology of the space. Is there any way to extract that information? Or can you speak to the topological aspects of the problem?
Yeah. So I think in terms of our method for the topology learning, we're really mostly using that in learning the latent space for the navigational memory, in that it's basically just mapping image features that occur closer together in the latent space. And so it's learning in that way, like, oh, these two objects like appear close together. But we're not doing any of that learning explicitly. It's all kind of implicit learning. But I think there are a lot of other methods that are trying to learn more explicitly, like the patterns of a house, right? Like kitchens are currently here, usually here off of the living rooms, and then they have, you know, all of the like bigger appliances and things, and then reasoning over that as well.
Okay. Another question from an anonymous attendee. what is the work's performance against existing visual navigation foundation model?
So we compared ours to NRNS like I showed a little bit earlier.
Right.
I'm not sure if there is like a foundation model that people are really using for visual navigation.
Yeah, I'm not aware either of a foundation model yet.
Yeah.
Maybe next month.
Maybe that'll be next.
Okay, so the next question from Troy Williams. How could this method be adapted to other situations? For example, an autonomous car driving in cities or an emergency response robot that needs to navigate crowded areas or disaster zones.
Right. So I think to answer this, it's really the strength of this work is in how modular it is, and that if you want to specialize it to something like specifically autonomous driving in cities or working in a disaster zone, you can kind of pick and place each module for either like the high level manager, or like maybe you want to have a different memory implementation, or for like our low level worker, we're not really doing any learning there at all. And so like there's a lot of different areas that would be open to kind of customizing it for your different solutions or your different problem areas.
Okay, the anonymous attendee said to us that the model is the VINT. It says VINT is the foundation model.
Oh,
But thank you for answering. Then he
great.
gives a link of a paper on archive.
Okay. I will definitely take a look at it.
Foundation model for visual navigation.
I haven't seen it yet, but I'll definitely take a look.
Yeah, I wasn't aware of that paper either. It's a 2023 paper.
Okay.
Okay, very good. And
Thanks.
thank you, anonymous attendee, for giving us this information. Okay, so the time now has come to 3 o'clock, and I would like to thank again the speakers, Chahatdeep Singh and Faith Johnson.